For 60 years, every fighter jet launched from an American aircraft carrier was thrown off the deck by a steam-powered piston. 520 pounds per square inch of superheated steam slammed into an 18-inch cylinder, accelerating a 45-ton aircraft from 0 to 170 miles per hour in 2 seconds across 300 feet of deck. It worked. It launched hundreds of thousands of aircraft across 11 carriers and 6 decades of service. Then America ripped it out and replaced it with a magnetic wave. Not because steam was broken, because the next generation of aircraft that will fly from carrier decks cannot survive a steam launch. This is the engineering of why America replaced the most proven launch system in naval history with an electromagnetic rail that had never been tested in combat. Launching a jet off an aircraft carrier is one of the most violent engineering problems in aviation. A fully loaded FA-18E Super Hornet weighs roughly 45,000 pounds and must reach approximately 150 knots before it rolls off the bow, or it stalls into the ocean ahead of a 100,000-ton ship that cannot stop in time. The kinetic energy required is approximately 133 megajoules, delivered in about 2 seconds. The aircraft engines at full afterburner contribute only about 14% of that energy. The Catapult must supply the other 86%. For 6 decades, the Nimitz-class C-13-01 steam catapult handled this job. It is a twin-cylinder steam piston with an 18-inch bore and a 309-foot power stroke, fed by a wet steam accumulator bled off the nuclear reactor's secondary loop at 520 psi. Each launch dumps approximately 1,350 pounds of superheated steam into the cylinders, driving paired pistons coupled to a shuttle that connects to the aircraft's nose gear through a slotted trough in the flight deck. At the end of the stroke, the pistons slam into water brakes that absorb 176 Gs of deceleration. The system draws roughly 1,389 megajoules of thermal energy from the accumulator to deliver only 95 megajoules of useful kinetic energy to the aircraft. That is approximately 5% thermodynamic efficiency. But the fundamental problem with steam catapults is not efficiency. It is physics. Steam is a fixed mass of gas expanding into a growing volume. As the piston moves forward, the volume behind it increases and pressure drops according to thermodynamic expansion laws. Force equals pressure times piston area, so force peaks in the first 10% of the stroke and then decays for the remaining 90%. The peak-to-mean acceleration ratio is 1.25 under normal conditions and can spike to 2.0 in off-nominal launches. That means the aircraft absorbs its highest structural stress at the very beginning, when the airframe is most vulnerable. There is no closed-loop feedback during the 2-second stroke. A capacity selector valve is set manually before each launch based on aircraft weight and wind speed. Too little steam, and you get a cold catapult shot where the aircraft rolls off the bow below stall speed and ditches into the ocean. Too much steam, and you shear the nose gear off the airframe. For 60 years this worked because every aircraft launched from a carrier was heavy enough to absorb the peak force without breaking. But the aircraft coming next are not heavy enough. A drone weighing 1/10 of a Super Hornet would be torn apart by a steam catapult set to its minimum energy. America needed a catapult that could launch anything from a lightweight drone to a fully loaded fighter. Steam cannot do that. Electromagnetism can. The Electromagnetic Aircraft Launch System, called EMALS, is built by General Atomics. It is essentially a rotary electric motor sliced open lengthwise and unrolled into a 91-meter linear track beneath the flight deck. Two parallel rows of stator coils run along the track. The aircraft shuttle contains a 22-foot aluminum reaction plate that rides between the two rows of coils, with a gap of just 6.35 millimeters on each side. When three-phase alternating current flows sequentially through approximately 149 stator segments per side, it creates a traveling magnetic wave that slides down the track. The coils do not move, only the wave moves. That wave induces eddy currents in the aluminum plate through Faraday's law of electromagnetic induction. Those induced currents create an opposing magnetic field through Lenz's law. The Lorentz force between the two fields drags the shuttle forward in lockstep with the wave. Only the coils immediately surrounding the shuttle are energized at any instant. They are switched on and off by thyristors, receiving position data from Hall effect sensors thousands of times per second. Because force is generated by electrical current rather than steam pressure, the force profile is entirely software-defined. A cycloconverter adjusts the waveform in real time to hold the peak-to-mean acceleration ratio at 1.05 compared to steam's 1.25. The launch is smooth and controlled from the first inch to the last. Navy fracture mechanics analysis shows this extends airframe fatigue life by 31%. And because the energy is tunable in software, the Electromagnetic Aircraft Launch System, EMALS, can deliver anything from a gentle push for a lightweight drone to a maximum energy launch for a fully loaded Super Hornet. The same track, the same motor, the same software, just a different number entered into the control system. But there is an engineering problem that nearly killed the entire program. EMALS needs up to 122 megajoules per launch, delivered at a peak power of 60 megawatts for 2 to 3 seconds. No ship in the world can supply that directly from its electrical grid. General Atomics solved it with kinetic energy storage. The ship carries 12 disk alternators organized into 3 energy storage groups. Each rotor is forged from Inconel superalloy, weighs approximately 80,000 pounds, and spins at 6,400 RPM between launches, storing 121 megajoules of energy per rotor. Counter-rotating pairs cancel gyroscopic torque, so the spinning mass does not try to steer the ship. During a launch, the rotors switch from motor mode to generator mode. A cycloconverter reshapes the alternator's 2,133 Hz output into a rising waveform from 0 to 644 Hz that matches the shuttle's accelerating speed. The rotors spin down from 6,400 to approximately 5,205 RPM in 2 to 3 seconds, converting their stored rotational energy into electromagnetic thrust. The ship's grid then respins the rotors in about 45 seconds, ready for the next launch. End-to-end conversion efficiency approaches 90% compared to steam's 5%. To feed EMALS and every other electromagnetic system on board, the USS Gerald R. Ford's 2 Bechtel A-1B nuclear reactors generate 300 megawatts of electrical power, roughly 3 times the output of the Nimitz-class A-4W plant. The Ford displaces 100,000 tons, stretches 1,106 feet, cost $13.3 billion, and was commissioned on July 22, 2017, as the most expensive warship ever built. It carries 75 aircraft and reduces crew by approximately 600 sailors compared to the Nimitz class. It targets a sustained sortie generation rate of 160 launches per day, a 33% improvement over Nimitz. The entire ship was redesigned around electricity, but none of those numbers mattered when the system started failing. The original reliability target for the Electromagnetic Aircraft Launch System, EMALS, was 4,166 mean cycles between operational mission failure. Early testing achieved just 181, roughly 4% of the target. The system suffered from a shared power architecture where 4 catapults feed from 3 energy storage groups that cannot be electrically isolated during flight operations. Spinning down a flywheel for maintenance takes 90 minutes. President Trump publicly criticized EMALS, saying, "You had to be Albert Einstein to understand it," and calling for future carriers to return to steam. But the Navy kept iterating. By February 2024, EMALS had completed over 22,900 successful launches and recoveries, with 8,725 catapult shots during the Ford's first full deployment alone. Mean cycles between failure climbed from 460 to 614, still below the 4,166 target, but nearly 4 times the initial 181. The system was proving itself through sheer volume. Then came the test that no amount of peacetime launches could simulate. On February 28, 2026, Operation Epic Fury began. The USS Gerald R. Ford deployed to the Eastern Mediterranean as flagship of Carrier Strike Group 12. For the first time in history, electromagnetic catapults launched combat strikes in a real war. Super Hornets and Growlers launched from EMALS catapults during the opening night strikes against Iran and throughout the 38-day campaign. The Ford eventually broke the post-Cold War deployment record at 295 continuous days at sea. EMALS had proven it could fight. But the real reason America replaced steam is not about today's fighters. It is about tomorrow's drones. The MQ-25, a Stingray tanker drone, begins fleet operations in 2026. Future CCA autonomous combat drones will follow. Steam catapults cannot safely launch these lightweight unmanned aircraft because even the minimum energy setting is violent enough to damage their airframes. The Electromagnetic Aircraft Launch System, EMALS, simply programs a smaller electromagnetic pulse, the same track that throws a 45-ton Super Hornet at 170 miles per hour can gently push a 5-ton drone to its takeoff speed without breaking a single structural member. The carrier air wing of the 2030s will be a mix of manned fighters, unmanned tankers, autonomous combat drones, and unmanned surveillance aircraft. Only EMALS can launch all of them from the same deck. And America is no longer alone. China's Type 003 Fujian carrier was commissioned in November 2025 with its own electromagnetic catapults, making China the second nation with operational electromagnetic launch capability and the first to launch a 5th-generation fighter from one. France's next carrier will carry 3 EMALS units under a General Atomics contract. The electromagnetic catapult is not just America's future, it is the future of carrier aviation worldwide. Steam served for 60 years. It launched hundreds of thousands of aircraft, but it cannot launch the aircraft that come next. That is why America replaced it. For 60 years, steam threw jets off carrier decks with a 520 pounds per square inch piston and 5% efficiency. Then America replaced it with a magnetic wave, 12 spinning rotors, and a line of software code that tells the catapult exactly how hard to push. Not because steam was broken, because the next 60 years of carrier aviation cannot be launched with a piston.